Bana bir e-mail at. Okay, so let's start. We have seen existence, uniqueness part and continuous dependence on initial and boundary conditions of the heat equation problem. We will see now existence and the method to construct the solution is separation of variables. This method is not only applicable to heat equation, but all the actually linear second order equations. So basic idea is this. Look for solutions of the form uxt, which is written as the product of two functions, two one variable functions. One of them is a function of x and the other one is a function of t. Okay, now well, we are of course looking for a solution of the following problem. We had a differential equation, namely the heat equation. And then we have boundary conditions. For time being, I'll consider homogeneous boundary conditions. And then we have initial condition or initial temperature distribution, which is given like this. Here, t is between 0 and infinite. And here, x is between 0 and L. So here is the problem. We have a, let's say, object of length L. We keep the temperature at the endpoints at 0 Celsius degrees at all times, okay, for all times. And initially, temperature distribution is given like this. So from 0 to L, it is given by some function. So we have initial temperature distribution of this object at time 0. And then we put two, let's say, ice blocks so that we keep the temperature at the both ends at 0 Celsius degrees. And then we would like to know what the temperature is at any time and at any time and at any point. So uxt is the temperature at the point x and at time t. Right, the uxt is the temperature at x at position x at time t. But to keep life simple, first we assume that our solution has this form. Okay. Of course, we will see that the solution we will obtain will not be like this, but we will see that actually solution gelebilirsin. the solution will be just some of these kind of solutions. Note that both boundary conditions and the equation are homogeneous. Therefore, we can add solutions, and the sum of solutions will be again a solution. All right. So we assume that our function has this form. Then, so let me write it like this: x of x and t of t. Then what would be the x derivative of this? Well, x derivative of this is just the x derivative of this function, and we write just x prime because it's a single valued function. So x derivative of this is just x prime times t. What about the second derivative with respect to x? Well, I'll take derivative one more time, so it is this. And then u sub t, xt is just x of x times t prime t. All right. Now let's plug this 3 into this equation. So u sub t is just x of x times t prime is equal to alpha squared u sub xx. Well, that is just x double prime of x times t of t. All right. Well, I guess it is clear why we call this method separation of variables, because in the solution we ask the variables x and t are separated into two functions, and it's in the product form of those two functions. And then we do the following. Once we have this, you see, I can collect x and t terms on separate sides. I have x double prime. Bakayım bunu nasıl yazıyoruz? Okay. X double prime over x. So I just take this x here, and then here I have t prime over alpha squared t. And then we do the following. Of course, this is true for all x and for all t. Okay. Well, this function here, it's a function of x only, and this is a function of t only. So this is a function of x, and this is a function of t. Well, of course, I can do the following. I can change x, but keep t fixed. As t kept fixed, this will not change. But as I change x, this should change. But they are equal, therefore it cannot change also. This means what? This thing is a function of x, but actually it's a constant function, because as I change x, it won't change because I am not changing t. So it means that this is a constant function, and this thing is also, of course, a constant function by the same reason, and these two constants are the same. So this means what? So there is a constant, say lambda, o bakayım nasıl yazıyor şeyden, c demiş ama biz lambda diyelim. Lambda, so that x double prime over x t prime over alpha squared t is equal to both, let me say minus lambda, okay? For some, technical reasons, it is better to write it this way. Okay. Now, and this is true for all x and t. Aslında denklemde bunları şey yaptık değil mi? Neyse fark etmez. Şimdi bakın ne oldu? But you see now, of course we don't know what is this constant, okay? We don't know what this lambda is. It is a constant, but we don't know what it is, okay? However, problem is reduced to ordinary differential equations. We have two equations. X double prime over x is equal to minus lambda, and t prime over alpha squared t is equal to minus lambda. So this gives two ordinary differential equations, right? Namely, first one is just minus lambda, or I have this, and t prime over alpha squared t is minus lambda, or t prime plus lambda alpha squared t equals 0. So we have two ordinary differential equations, and we know how to solve them. Okay. Now let's start with the first one. Aslında belki ondan önce bir de boundary condition'lara bakalım. Now let's also see what happens to the boundary conditions under this assumption. Okay. So let's see boundary conditions. The first boundary condition is this: 0 is equal to u0 t. Well, that is just x of 0 and t of t. And this is true for all t, right? Well, you see, this is a constant number and this is a function. If this constant number is not 0, then this function would be 0. But then our solution uxt would be 0 because this is 0. So I would just get 0 solution. But the 0 function, although it satisfies this one and these two conditions, it doesn't satisfy this one, because f is an arbitrary function and it doesn't have to be 0. Therefore, that option doesn't give us anything interesting. So the conclusion is this: if this is not 0, then so t of t would be 0 for all t, and this would imply x t would be 0 for all x and t, and we don't want this, which is not desired. Yani çünkü bu denklemin çözümünün sıfır olmadığını biliyoruz, değil mi? Just maybe you heated the metal bar up to 100 degrees and then you let it cool down, but temperature of course will drop, but it won't be 0 at all times, right? So 0 is not the solution. Therefore, we should assume that, hence we should take x of x equals 0. Otherwise, we don't get anything interesting. Okay, so we should take x of x 0. Well, of course, this same argument applies to the other boundary. Namely, şunu kapatayım ya. Parlıyor sanki. Şöyle olsun. Daha iyi mi? Okay. All right. Similarly, the other boundary condition, which is LT, would give us x of L, T of T. And again, if this is not zero, then this function would be zero, and so on. The same arguments would imply. X of L is zero. Sir. Uh-huh. Yani diferansiyel denklemin şöyle onu yani içerideki noktalara işte soldan veya sağdan boundary'deki noktalara yaklaşamadığımız için hani o türevi oralarda hesaplamıyoruz. Ama onun dışında hesaplıyoruz. Peki. Şimdi o zaman for x of x we have what? We have the following. We have this ordinary differential equation and two boundary conditions. Note that this is not an initial value problem. This is a boundary value problem, right? We are looking for a solution of this equation so that at the 2 points at the end of the intervals, these two are equal to 0. All right, how can we solve this? Well, we have second order equation, so let's solve this problem. We write down its characteristic equation. It's a constant coefficient equation, and the characteristic equation is just r squared plus lambda equals 0, right? Well, so we have r squared is equal to minus lambda. Depending on lambda, this will have different kinds of solutions. So we have cases. Case 1, let's say this is negative. If it is negative, then r squared, which is minus lambda, is positive. Therefore, we have two real roots. What are they? They are square root of minus lambda and minus square root of minus lambda. Therefore, x of x is just c1 times e to the power, let's say r1 x plus c2 e to the power r2x, but r2 is just minus r1x, right? All right. Now, let's try to find C1 and C2. Well, we use boundary conditions. Sıfır koyarsak, if we plug 0 for x, we get C1 plus C2. And then we have also this condition. So C1 e to the power minus what? R1 L plus C2 artı, evet, minus R1L. Okay. Now, this equation, right, gives us C2 is just minus C1. And let's plug it here. 0 is equal to C1 e to the power minus, no, R1L plus, instead of C2, let me write minus C1 e to the power minus R1L. Well, you see, what is this? This is just C1 times e to the power R1L minus e to the power minus R1L. L is a positive number. R1 is a positive number. It is positive square root of minus lambda. So this is a positive number. Therefore, this number is larger than 1. E to the power, a positive number, is larger than 1. This is just 1 over this number. So whatever this is, let's say this is A, which is larger than 1. This thing is 1 over A, and it is less than 1. One of them is greater than 1, the other one is less than 1. Therefore, this number, whatever it is, it cannot be 0. But the product is 0, right? So this number is not 0, but the product is 0. So this implies this C1 is 0. Well, then, of course, C2 is 0. So we get, again, U equals, sorry, x of x is just the 0 function because both coefficients are 0. Therefore, uxt would be just 0. So this gives us nothing but the 0 solution, and that's not, of course, what we are looking for. Sor. Hı hı. Burada muhtemelen maksimum ya f'in maksimumu olacak, f pozitifse, bir ya da 0 olacak. Evet, evet, öyle olacak. Ee, Yok. Şimdi ne elde ettiğimizi görünce hani oradan çıkmayacağını anlayacaksın. Okay. So, ha mi diyorsun? Bu çözümün 0 olacağını öyle doğrudan mı görebiliriz? Yani şimdi şurada 0 çözüm elde ettik ki, onu mu söylüyorsun? Neyse, yani yapalım. So the second case is, here we took lambda negative. Now let's see the case lambda is 0, and then we will consider the third case. Now, then the characteristic equation, which was this, right? And it is 0. So we get R1 and R2 are both 0. So so what are the solutions? E to the power 0x, which is 1. And since it's a double root, x times e to the power 0x, which is just x. Therefore, x of x is just C1 times the first solution, which is 1, plus C2 times the second solution. Okay? Well, let's find C1 and C2 again. Again, I will use the boundary conditions. 0 is equal to x of 0. So if I plug 0 here, I get, of course, just so C1 times C1 plus C2 times 0, which is just C1. So C1 is just 0. And what about the other one? X of L, C1 plus C2 times L. But this is already 0, so this, right? So this is just C2 times L. Therefore, L is, of course, the length of the interval. So this is a positive number. Therefore, we get, again, C2 equals 0. So both coefficients are 0. Therefore, again, x of x is just the 0 solution. So this doesn't give us anything interesting either. So we keep the interesting case to the last. Okay, lambda is positive. Let's see what we get. So this time r squared is minus lambda, and it is negative. So what is r? R is just square root of this negative number. So it is plus minus I times mu. What is mu? Mu is a positive number, so that mu squared is lambda. Okay? Square root of minus lambda, where lambda is a positive number, is purely imaginary numbers, I times square root of lambda. So let me just keep it like this. Now, what are the corresponding solutions? Since these are purely imaginary, we, well, since they are non-real, we obtain sine and cosine, right? So what are the, yani şöyle olsaydı, if I had roots like this, what would be the solution? It would be e to the power ax cosine bx and e to the power ax sine bx, right? That would be the solutions for this kind of roots for the characteristic equation. In our case, there is no real part. So the solutions we obtain are just C1 times A is 0, B is just mu, so we have cosine mu x plus C2 sine mu x. Okay. Well, what are C1 and C2? So we again use the boundary conditions. Okay, let me rewrite what we have over there. So we have x of x, C1 times cosine mu x plus C2 times sine mu x. And the initial conditions are x of x, x of 0 is equal to 0, and x of L is 0. X of 0 is 0 gives us what? 0 is equal to, when I plug 0 here, I get 0 here, so C2 disappears, and I get 1 here, so this is just C1 times 1 plus C2 times 0, so this is just C1. So this gives us that x of x cannot contain any cosine term, only sine. So this is C2 times sine mu x. Okay. Now what is C2? Well, I have another boundary condition, which is this. So let's plug that one also. Sine mu L. All right. So what we have seen now is interesting. I have two real numbers in product form. The product is 0. So either this is 0 or this is 0. If C2 is 0, then this would also disappear. Therefore, I would get again the 0 solution. So if sine mu x is not 0, then C2 would be 0. So that again x of x would be just the 0 function. And this would give us again the 0 solution here, which is not interesting. Therefore, this gadget should be 0. So to obtain non-trivial solutions, we must have what? This sine mu L is equal to 0. Well, when this is possible, it is possible only if this number is an integer multiple of pi, right? So mu times L should be an integer multiple of pi for k equals z. Therefore, mu is just k pi over L. And therefore, lambda was mu squared. So it is just k pi over L squared, where k is an integer. But you see that since I am taking square, minus negative integers won't give us anything new. And k equals 0 gives me lambda equals 0. And if, it gives us mu equals 0. And if mu is 0, again, I get the 0 solution. So, okay, I can, enumerate them like this. So we get these solutions. Xk of x is just some number times sine mu k. So it is just k L over L x. And as I said, okay, so if you choose negative integers, minus sign just goes out, but I will put a constant in front of this already. So that minus sign is absorbed by this constant. And if you plug 0, you get the 0 solution, so you don't get anything interesting. Therefore, I may just take only the positive integers. So for each positive integer, I have one solution. And since I will put constants later, I can just leave it like this. And here, lambda k, for each k, lambda k is just k times pi over L squared. I should keep track of this lambda. Why is that? Because you see, I use the same lambda for x and t. Okay, so for this lambda, if I obtain some x, for the same lambda, I should obtain a t, and then my solution would be just the product of x and t. Okay, u was, remember, use x times t, but I should use the same lambda for both of them. Okay. All right. Now let's consider the second equation. What is the second equation? It is this one. T prime plus lambda alpha squared t equals 0. And what is lambda? Lambda was an arbitrary constant at first, but now we have seen that lambda cannot be an arbitrary constant. Lambda is just k pi over L squared, and k is 1, 2, 3, and so on. Okay. Now for this lambda case, I will solve this equation. So let me label this as lambda k, and for each lambda, of course, I will get one solution, and let me also label the solution with k also. Değil mi? Her bir lambda için, her bir k için bir lambda k var ve bir denklem var. O denklemin çözümüne de tk diyeyim. Peki bunun çözümü ne olacak? Well, this is the first order equation, right? I can write it like this. So this is dtk over dt is equal to minus lambda k alpha squared tk, and I can write it like this: dtk over tk is just minus lambda k alpha squared dt, and then we integrate both sides. Here we get lambda tk, I mean not ln absolute value of tk is equal to integral of this minus lambda k alpha squared plus a constant, and then from this, efendim, evet t var plus c. Okay, yeah, so, and when you exponentiate this, you get what? E to the power c here, e to the power minus lambda k alpha squared t. This is another constant. It's a positive constant, but I have, absolute value here. So if I drop the absolute values, I may let this number to be negative. So let me just keep it like this: e to the power minus lambda k alpha squared and then t. So that would be the solution. Of course, I can write it like this, but let me let tkt, let me just take this constant to be 1 for time being. Later I'll multiply this by arbitrary constant. So let me just do it like this. Lambda k is is what? N pi over, not n pi, k pi over L squared alpha squared t, and therefore u x t, which was x of x plus t of t, but for each positive integer, I have one x and one k, one t. So let me just label them like this. Therefore, this is just k. So 1, 2, and so on. And uk is just what? This is e to the power minus k pi over l squared. Aslında bunun içine alfayı da koyabilirim. Değil mi? Şöyle yapayım. Alfa squared t sin n k pi over l x. Okay. So we obtained solutions as we taught at the beginning. It's a function of t and times a function of x. Okay. However, this thing, of course, will not satisfy the initial condition. What was the initial condition? It was this. So when I plug t equals 0, here I will get, this would be just 1. So sine k pi x over L. And of course, that won't be equal to f. But the observation is the following. Now, for each positive integer, I have a solution of the differential equation and the boundary conditions. And we note that, so this uk xt satisfies both the PDE, which is u sub t minus alpha squared u sub xx equals 0, which is an homogeneous equation, and the boundary conditions, which was u0 t equals 0 and u lt equals 0. For all k, and what we do is the following. We just take arbitrary linear combinations of this UKs. Okay. Bunu mu? Bunu da kaldırayım. Okay. All right. Now, note that since the PDE, heat equation, and boundary conditions are all homogeneous, arbitrary linear combinations, of course, I mean, if the sums are assuming the sums are convergent, arbitrary linear combinations of the form. Yani şöyle şeylere bakarsak, B and T and T, X and T, and from 1 to infinity. Değil mi? Her birisi bunların bir çözümdü. This is U and T, U and XT, right? This is a solution. Each one is a solution, and their arbitrary combinations are also solutions. And actually, we can take sums, okay, like this. So are also solutions. So let's take uxt. So this is the general solution. B and then t and t, x and x, and from 1 to infinity. And b and z are arbitrary numbers, so that this thing is convergent. Tamam mı? Bunu yazarsak, yani bunların her birisi çözüm olduğu için, denklemimiz de homojen olduğu için bu tip toplamlar da convergent oldukları sürece çözüm olacaklar. Peki nedir bu? So this is what? This is just minus, let me just use n instead of k, n pi alpha over L squared, right? T sine n pi x over L. Okay. Now, I still haven't employed the initial condition. What was our initial condition, right? I need to figure out this B ends. Anyway, suppose, consider the heat problem. We heated up, this metal bar to some temperature at any point, and then we keep the temperature 0 Celsius degrees at this point, and then we just let it cool down. Of course, temperature will change in time, but it should, behave. There should be a unique solution. Therefore, I should be able to find this BNs. How can I find those BNs? Well, to determine BNs, I will use the initial condition which I haven't used so far. What was the initial condition? F of x is equal to u x 0. Well, if I plug 0 here, I get e to the power 0, which is just 1. Therefore, we get bn sine n pi x over L. Can I solve this equation? Yes, we have seen such things before, right? This thing is just a sine series for this function. Can we find a sine series for the function? Well, of course we can. This is the function on the on the interval 0L. I will extend this function to minus LL as an odd function, and then I will compute the coefficients, right? So the series is just the sine series, sine Fourier series for the function f defined on this interval, right? Doğrudan katsayılarını da yazabilirim. Neydi? Bn. Recall that. This equation gives us the coefficients right away. What were they? 1 over L or 2 over L? 2 over L, değil mi? 0 to L, f of x sine n pi x over L dx. So you just compute these and then form the series. Let's see one example, but okay. Zamanı var mı? Yokmuş. Okay, let's give a break. After the break, I'll continue.